Welcome again. Today we will teach ETAR reaction and also DMSO based oxidation reactions. So, first we will discuss ETAR reaction. ETAR reaction is the direct oxidation of an aromatic or heterocyclic bound methyl group to aldehyde group. Like here, toluene derivative is oxidized with chromyl chloride to the benzaldehyde derivative, and you have to use DCM solution because otherwise the reaction is very vigorous, and under this condition toluene derivative can be oxidized to benzaldehyde derivative. Also there is another reagents, chromium trioxide and acetic anhydride mixture can also oxidize toluene derivative to benzaldehyde. Here the chromium trioxide acetic anhydride generate this diacetoxy derivative, and which after acidic hydrolysis can generate the benzaldehyde derivative. And if you see the chromyl chloride structure, this is like this. Here also if you consider the oxidation number, it is +6 also. And now we will discuss the mechanism of this reaction. There are two well accepted mechanisms. First is the in way. So, here the toluene derivative and this is the chromyl chloride. First this in type reaction can happen to generate this chromium compound, and this chromium compound then can undergo 2,3 sigmatopic rearrangement like this. This is 2,3 sigmatomic rearrangement because only 5 atoms 1, 2, 3, 4, 5 atoms are involved, and then you get this alkoxy chromium compound, and this compound, this acidic hydrogen can be deprotonated by Cl minus, and this chromium can be withdrawn from the complex to give this benzaldehyde. Alternatively, there are again this possibility further in reaction and sigmatopic rearrangement which can generate this acetal derivative, and which can react further with water. Suppose water reacts with chromium here, and then this alkoxy compound is formed, which after elimination can give the benzaldehyde. So, here just I will tell the another mechanism which is possible and which was earlier proposed by the authors, that this kind of benzylic radical can form, and here this and then this can react to this radical, and which will form this intermediate. So, either by radical possibility or by in mechanism we will generate this alkoxy chromium intermediate, which after hydrolysis or further reaction this acetal chromium complex, and that also will give the benzaldehyde. However, there are limitations for this reaction. One limitation is the multiple products will form when you increase the chain length. Like if you use N propyl instead of methyl, if there is a N propyl group, then there are many products formed. And if we consider the radical mechanism, here the benzylic radical will form, and this will be byproduct, and now this radical can react again to give this compound a chromium complex, as well as chlorine can react to give this chlorine compound. This was also side product of this reaction. Now, this one, as we discussed earlier, this can further react with chromyl chloride to generate this acetyl chromium complex, which after hydrolysis generate the desired product. So, this is the desired product, that the benzylic CH is getting activated and it goes to the carbonyl compound. So, this ketone is formed. However, there is also possibility for the elimination reaction to generate this olefin, And this olefin further reacts with chromyl chloride, and after hydrolysis it can generate this benzyl methyl ketone, where the this carbon is activated and you get the ketone, which is benzyl methyl ketone here. Now we will discuss DMSO based oxidation, activated dimethyl sulfoxide. As you know, DMSO is used as a solvent in general in the lab, but it has also used oxidizing reagent. So, that we can discuss now. So, DMSO this will be resonance. So, DMSO can resonating from like this one, and this is a electrophilic So, this is the electrophilic center, and that is why scientists thought that alcohol can be reacted at this electrophilic center, but for that, since O minus is a leaving group, this group has to be modified, and that is why they reacted first this one with electrophile, which gives you this electrophile, which we can write S plus X, where X will be actually a leaving group. Now, if you react with alcohol, or at dash you can call, so this sulfonate salt is formed, actually X minus can be there here. And now, in general with base, so base what it does, it can either activate at this one, it can generate negative charge, and then it can form this ketone, and you get DMS. So, dimethyl sulfoxide ultimately is going to dimethyl sulfide. So, it is getting reduced, and if you consider carefully, this alcohol OH actually here it is reacting as a nucleophile, and so the main strategy that you generate this electrophilic species. So, main electrophilic species, and then you have to react with alcohol, and also you have to use a base which will deprotonate this or this, ultimately carbonyl compound will form and dimethyl sulfide will be a byproduct. And different electrophilic reagents have been used for this first reaction with dimethyl sulfoxide. So, that we will write now, like electrophilic species can be SOCl2, chlorine, it can be N-chlorosuccinamide, it can be oxalyl chloride, it can be tosyl chloride, acetic anhydride, etc. Also, not only alcohol, this strategy can be used other oxidation also, like normal alcohol, phenol, amine, also oxime compound can also be used for oxidation in these strategies. And there are many name reactions like which we will discuss now, like Kornblum oxidation, because there are different electrophilic reagents can be used, and that is why different name reaction came out, like Kornblum oxidation, Barton modification of Kornblum oxidation, then Moffat-Pfitzner oxidation, Parikh-Doering oxidation, Corey-Kim oxidation, Swan oxidation. There are two variants. First developed was with trifluoroacidic anhydride, and later they modified with oxalyl chloride, which is called the Swan oxidation. That is what the familiar Swan oxidation uses oxalyl chloride. So, dimethyl sulfoxide mediated oxidation. First we will discuss Kornblum oxidation. This oxidation was discovered in 1959. A primary tosylate is heated at 150 degree centigrade to cause SN2 displacement by the oxygen of dimethyl sulfoxide in the presence of sodium bicarbonate. So, this is very harsh condition, and we can see an example like this tosylate, and here this tosylate you can easily obtain from the alcohol 1, 2, 3, 4, 5, 6, 7 like heptanol, and then you get the tosylate. Now, if you heat with DMSO, then you get the displacement and you get this sulfinate salt. Now, if you put sodium bicarbonate in the sulfinate salt, then this acidic hydrogen, this gets deprotonated by the sodium bicarbonate anion, and you get the aldehyde N heptanol plus dimethyl sulfide. So, this is an early example. Also, you can see that this oxygen is coming from the DMSO. So, if you put this O18, then this aldehyde will be O18. Also, Kornblum shown that you can use alkyl bromide also, and alkyl bromide similarly with reaction with DMSO we will do an SN2 substitution, and you get the sulfinate salt. And now, if you put sodium bicarbonate, here we have used pentyl bromide. So, if you use sodium bicarbonate, then you get the elimination of DMS, and you get the one drawbacks of this reaction was that high temperature. So, Barton modified this reaction, and Barton discovered this modification in 1964. They are able to generate sulfinate salt by treating alkyl chloroformase with DMSO with loss of CO2. Addition of triethylamine, instead of a inorganic base, they use organic base like triethylamine, which generates the oxidation product, and this procedure ameliorated the harsh condition of the Kornblum procedure. And the chloroformate is readily available by treatment of the alcohol to be oxidized with excess phosgene. Here actually you can earlier what we have to make the tosyl derivative, here you have to generate this chloroformate derivative, and this you can generate easily by treating with phosgene. So, if you treat with phosgene the alcohol, then you get this chloroformate. Now, DMSO reacts, and DMSO reacts first and to generate this derivative. And now, this derivative you can see that this oxygen can react with here, and carbon dioxide can eliminate, and after carbon dioxide elimination you get the sulfonate salt. That was the main electrophilic species we have seen here. And now this one, after triethylamine, after triethylamine basic condition, it can generate the carbonyl compound triethylammonium hydrochloride salt and dimethyl sulfide. Now another oxidation was Pfitzner-Moffat oxidation. It was discovered in 1963. Here dicyclohexyl carbodiamide, DMSO, and a proton source was used. Primary alcohol can be oxidized to aldehyde to ketone. Although phosphoric acid, generally phosphoric acid is used here, the proton source. Phosphoric acid is an effective acid catalyst for this reaction. Sulfuric acid, hydrogen chloride, trifluoroacid, acetic acid are not. However, pyridinium trifluoroacetate is an effective catalyst. This is the standard condition that DCC DMSO and H3PO4 and DCC. This is the DCC structure, dicyclohexyl carbodiamide, DMSO and phosphoric acid. And under this condition, you can selectively oxidize primary alcohol. So, here if you see this complex structure, here you have a acetate group, here tetrahydrofuran motif, and these groups are not disturbed. You can selectively get oxidation of the alcohol to the aldehyde. Also, you can see here a leaving group chloride is there, and OH, the secondary alcohol is selectively oxidized under this condition. Here that is what the pyridinium trifluoroacetate actually was used, the mixture of TFA and pyridine. This was also found to be a good proton source. Actually, this is mild compared to phosphoric acid and can give the product. So, what will be the possible mechanism for this reaction? So, DMSO can react first with the DCC. Actually, the DCC has to be activated with a acid, then only the DMSO can react. So, DMSO reacts at the carbon atom and of this diamide, and nitrogen is activated by the phosphoric acid, and you get after this you get this intermediate. And now the alcohol can be considered, it is deprotonated by the conjugate base of the phosphoric acid, that is the phosphate, and this nucleophilic reaction happens here, and also this imine bond is activated by the phosphoric acid, and after that you get this sulfonate salt, you get phosphoric acid back, and this is the urea, dicyclohexyl urea. And generally this precipitates in the reaction, and after that, since there is no external base, it is considered that the conjugate base of the acid, that is the phosphate, it actually acts as a base and deprotonates here, and you get the aldehyde, dimethyl sulfide and phosphoric acid back. So, that is why it is critical that the conjugate base of the acid should be basic enough to affect the last step of the reaction. This is very important. Otherwise, this desired transformation, without base, this sulfonate salt cannot decompose to the aldehyde and dimethyl sulfide. However, there is also drawback of this reaction, like separation of the byproduct dicyclohexyl urea and MTM ether formation can limit its usefulness. So, this we can discuss now. Actually, if you see this intermediate, or conjugate base, you get this one. This can be formed also. And then your alcohol can react here. So, this is a side product. So, that is why the MTM, this is the MTM ether formation. So, this is a side product of this reaction, because under acidic condition the conjugated base can generate this sulfonium cation, and where then the alcohol can react to give this ether. Another oxidation is Parekh-Doering oxidation, and here this compound was discovered in 1967. Here SO3 pyridine complex was used. SO3 pyridine is actually electrophilic species which reacts with DMSO, and triethylamine is the base. Here primary alcohol to aldehyde and secondary alcohol to ketone, and the oxidation utilizes the pyridine sulfur complex as the activator of dimethyl sulfoxide. Here are some examples. So, this reaction is quite mild. As you can see, there is a chiral center here, and the starting material E was 99.9% E, and after this reaction the aldehyde is formed, but the chiral center is not racemized under the reaction condition. So, generally this is room temperature, and under this condition the enantiomer selective vigor retained. Here also there is a secondary alcohol and there is a tertiary allylic alcohol. As we have seen, and this PCC oxidation, this compound can isomerize and give the ketone enone species. So, under this condition, Parekh-Doering condition, you can get selectively this secondary alcohol oxidation without disturbing this. So, this is very important, and we can discuss now the mechanism of this reaction. So, this is the SO3 pyridine complex. Now, DMSO reacts here. So, pyridine is out, and now you get your this sulfate. So, sulfate 2 minus is the leaving group here, and after that you get this sulfonate salt. Actually, here SO4 2 minus is the anion here, and now after treating with triethylamine, you will get the ketone and dimethyl sulfide and triethylamine ammonium salt. So, this is the reaction in all cases, that electrophilic sulfur species will be generated, and then the alcohol will react, and after elimination and formation of dimethyl sulfide you get the aldehyde or ketone. Korek group also discovered another reaction which is called Korek-Kim reaction, and interestingly he used dimethyl sulfide instead of DMSO. It was discovered in 1972. Here dimethyl sulfide NCS, this is N-chlorosuccinamide. So, this was used N-chlorosuccinamide, which is also electrophilic species, and triethylamine as the base. Primary alcohol also gets to aldehyde and secondary alcohol to ketone. In this procedure dimethyl sulfide is activated with N-chlorosuccinamide. When no base used, corresponding chlorides are formed. So, this is very important. If you do not use the triethylamine base, then you can use then the chloride will form, because chloride also is a good nucleophile. This is an example, and here they have used modified sulfide with a fluorine group, and under this condition N-chlorosuccinamide triethylamine toluene minus 25 degree centigrade, this nitrobenzyl alcohol is selectively oxidized to the nitrobenzaldehyde. So, here also we can discuss the mechanism. Here instead of DMSO you have dimethyl sulfide. So, dimethyl sulfide first reacts with N-chlorosuccinamide. Now, this group can also react, this group succinamidyl group can also react and generate this compound. Now, alcohol will react So, this is the intermediate in all our previous reactions, and now triethylamine. So, if we do not use the base here, then what will happen? This chlorine minus is present here. This chlorine minus can react here and generate the chloro derivative. Swan oxidation is very popular oxidation reaction. So, there Swan first developed a reaction which is called early Swan oxidation, that is discovered in 1976, and here trifluoroacetic anhydride was used as the activator and DMSO as and triethylamine base. Here also primary alcohol to aldehyde and secondary alcohol to ketone, and this early Swan oxidation employs trifluoroacetic anhydride at minus 50 degree centigrade to activate dimethyl sulfoxide. So, here also we can discuss the mechanism. Trifluoroacetic anhydride DMSO now alcohol will react. Trifluoroacetate is a good leaving group, and we get this species, and you get trifluoroacetic acid plus CF3 CO2 minus is there. So, this is the intermediate common in all previous reactions, and now triethylamine base, you get the ketone dimethyl sulfide and triethyl plus maybe CH3 Ca2 minus. Yeah. So, this was the early Swan oxidation, and later which is common as Swan oxidation, that is carbonyl oxalyl chloride as the electrophilic reagent. So, this was discovered in 1978. This is the oxalyl chloride, earlier was trifluoroacetic anhydride, here oxalyl chloride was used and DMSO triethylamine base. Generally this reaction occurs at minus 78 degrees centigrade. Here also primary alcohol to aldehyde and secondary alcohol to ketone. It is a convenient method for the production of DMS chlorine complex or intermediate without using dimethyl sulfide and chlorine. So, without using dimethyl sulfide and chlorine, we can get this DMS chlorine complex by oxalyl chloride. This is the standard condition, oxalyl chloride DMSO triethylamine alcohol will convert to the ketone. This is an example where there are many functional groups. Here an ketal motif is there, here a beta lactam motif is there, and you can see this selectively the alcohol, secondary alcohol goes to the carbonyl compound. Here an aliphatic long chain alcohol was oxidized with Swan condition, oxalyl chloride DMSO triethylamine minus 78 degrees centigrade, you get this aldehyde in good yield. Also in the presence of disulfide, disulfide is prone to oxidation. We know sulfide bonds can go cleave, also they can get oxidized to the sulfoxide, but under Swan condition this group is intact and selectively the alcohol groups is oxidized to the aldehyde. Also other acid sensitive group, if it is there like a cyclopropene ring, a double bond, and under this condition this structure selectively converted to the dialdehyde without breaking these motifs. The use of triethylamine can sometimes lead to the epimerization at the carbon alpha to the newly formed carbonyl. So, this one is a double bond is here, and under Swan condition it has been found that the double bond moved to this position, and to stop the epimerization it has been found that if you use strong base like diisopropyl ethylamine, which is called Honig base, and under Honig base condition if you replace triethylamine with Honig base, then you can stop this epimerization and you can get this product selectively. So, what is the plausible mechanism of this reaction? Here oxalyl chloride is a electrophilic species and DMSO can react here, and chlorine chloride minus will be as a leaving group, and you get this intermediate. And then the chlorine minus also is a nucleophile, and it will react at the sulfur atom and it will generate carbon monoxide, carbon dioxide, which liberates as gas. So, this process should be very facile to generate this chloro-sulfur complex. Now, alcohol will react with this electrophilic sulfur complex to generate this sulfonate salt, and after treatment with triethylamine, we can think that this proton might be more acidic. So, this deprotonate first, and after this helps to deprotonate this CH proton, and after that carbonyl compound will form and dimethyl sulfide will be a byproduct. In Swan oxidation, important of base. So, base is very important in Swan oxidation. Suppose if you use this allylic alcohol as the substrate, and in Swan oxidation condition oxalyl chloride DMSO dichloromethane triethylamine minus 70 degree centigrade, you get the alpha beta unsaturated aldehyde. On the other hand, if you do not put triethylamine the base, then what happens? Then under the similar condition like oxalyl chloride DMSO DCM and minus 78 degree centigrade, you get the allylic chloride. So, what is happening? So, when we have already seen in the mechanism that when you put oxalyl chloride and DMSO, you get this species sulfinyl chloride, and now the alcohol reacts with the sulphinyl chloride to generate the sulphinium salt. And now in the sulphinium salt we know that chloride minus is not good base, but good nucleophile. So, what will happen? The Cl minus, if there is no triethylamine, now the Cl minus will not deprotonate this H, instead it will do an SN to displacement reaction and you get DMSO here, you get DMSO back and you get the allyl chloride. So, that is the importance of base. So, without base in Swan condition you will not get the desired aldehyde, instead you will get the chloride. So, DMSO acetic anhydride is also an oxidation method. Here acetic anhydride and DMSO is used and generally primary alcohol to aldehyde and secondary alcohol to ketone. And in this procedure you can see that external base is not used. So, what will be the mechanism of this reaction? So, first DMSO reacts with acetic anhydride, if we write full also it will be like this, and now get the activated DMSO is formed plus OCOCH3 negative. And now alcohol like R1 OH, it reacts and you get R1 . So, this sulphinate salt is generated and there one molecule of acetate anion and another molecule of acetic acid is generated. Now, this acetate anion is basic enough to do the deprotonation. So, you get the carbonyl compound plus dimethyl sulfide plus acetic acid. So, this is the overall reaction, that acidic anhydride DMSO is also a good oxidizing reagent, and under this condition sulfoxide gets reacted with acetic anhydride to get this species, and now the alcohol can react. This is activated enough, now alcohol will react and generate this sulphinium salt, which on deprotonation by the acetate anion will generate the carbonyl compound and dimethyl sulfide, and acetic acid will be generated also. DMSO acetic anhydride is also has been used as a oxidizing agent, and this here instead of trifluoroacetic anhydride whatever we have seen earlier, here acetic anhydride and DMSO was used, and this also primary alcohol to aldehyde and secondary alcohol to ketone. So, in this lecture today we have first discussed the Etard reaction, which does benzyl methyl group like toluene compounds to the benzaldehyde, and then we have seen DMSO based oxidation reactions. First we have seen Kornblum oxidation where alkyl bromide or tosyl plate is used. Then we have seen the Barton modification where chloroformate was used. Then we have seen the Fridgen-Moffat oxidation where DCC and under phosphoric acid condition DMSO DCC can give the product. And then we have seen in the Parik condition SO3-pyridine condition, SO3-pyridine complex which activates DMSO and triethylamine base. This condition is very mild condition, and many natural product synthesis also this oxidation has been used. Also Core-Kim oxidation, which used the N-chlorosuccinamide as the electrophilic reagent, and instead of DMSO, DMS is used, and under this condition this electrophilic species generated which reacts with the alcohol to generate the aldehyde. Then we have seen the Swan oxidation. Earlier Swan oxidation was with trifluoroacetic anhydride, and later Swan developed the modified version, which is well known as Swan oxidation, where oxalyl chloride is used, and oxalyl chloride first reacts with the DMSO and to generate a intermediate, which after carbon monoxide carbon dioxide elimination generate the chloro sulfur complex. Then the alcohol reacts to generate the sulfonate salt, and after triethylamine reaction you get the aldehyde or carbonate compound. Thank you.